I hope you all managed to get coffee and get refreshed before we start. So today's talk is a continuation. Yesterday we were discussing transient surveys, mainly in visible light and optical. And today we'll cover all the other ranges of emission that you can use to find transients. Of course, this will make this review not extremely deep, because we have to cover many different observational techniques and results. To wake you up, I will start with a game. The game is called, there's two questions. First, okay, so the first question is which band or which wavelength these images are taken. You remember, if you remember, you probably don't, but yesterday my talk was, I began with the image of a supernova in visible light, that you can compare one image to the other and see the supernova. So this is not visible light. The question is which wavelength is that? We need to reduce the lighting a little bit so we can see properly. Okay. So, who knows? UV, right. Good answer. So this was taken in UV light by the Swift satellite. And you can see that in this galaxy, the UV enhances very strongly the areas of star formation, where you have many blue and hot stars. And now the second question and the interesting part is find the supernova. So, okay, you are looking, there are two images. One of them has an extra point, which is a new supernova. So to start with, I will not tell you which one has the supernova, and then if you don't manage, I will give you a hint. So now you are all playing Reverend Evans. Okay, so now the hint is in this image where the new star is. Which direction from the core? Right. Okay, good. Yes. Let's see if it works. Yes, here. So this spot here, you see it's missing here and it's here. Yeah. That's the supernova. Okay, so you can practice at home in finding supernova in the UV. So these are, as we said, these are observations from the Swift satellite. Okay, but we will not start with the UV, even though it's my favorite wavelength right now. We'll start properly from the lowest energies with radio transients. So this is maybe the part where I'll be the most condensed. So radio astronomy is a huge area, and searches for transients in radio have a long history. Not based on yesterday's definition, so transients are not variable sources, right? So sources that really have no quiescent counterparts. There are not many classes actually known of radio transients extragalactic, but the searches have been going on for many years. I will review mainly results from the Jansky Very Large Array. This is this array of very large telescopes in New Mexico, which is still currently the most sensitive radio instrument and probably the most widely used. I will say just now, basically, the only thing I'm going to say at lower frequency, this is mostly in centimeter wavelengths, so frequencies of order a few gigahertz. I'm going to say only one thing about searches in lower frequencies, mainly by this array, the LOFAR array, which you can see here. The LOFAR is centered in the Netherlands, You can see this is the typical radio telescope there. It's basically a swamp. And on the swamp, in the more dry places, they put these arrays. There are two kinds of arrays. These are like surface arrays, and here are fields of very simple antennas. And all of this works inside one of the most heavily populated areas of Western Europe with a lot of radio interference, and still they manage to do very nice astronomy from there, relying, of course, on very sophisticated noise reduction. So LOFAR searched very hard for transients, and so far, to the best of my knowledge, at least the published record is that they have one transient, which we don't know what it is. Maybe somebody will correct me if you know better. So there's not much to discuss, but certainly these low-frequency radio arrays are being developed in many places across the globe, and eventually I think they will find transients if they exist. And in the future, the square kilometer array, SKA, is going to be the mother of all radio telescopes. This is one of the precursors to that big array that eventually will be constructed in South Africa. And it will have the sensitivity of the VLA, but the field of view much larger. So basically, you can, for example, if this is what they want to do, and probably it's not what they're going to do, but you could have conducted an all-sky survey for transients every night at VLA sensitivity using SKA. They're not going to do it, but they could. So at the end, I will show you one thing that's related to these precursors that are already operating. Okay, now. Good question. It certainly could be as sensitive as the old VLA over all sky. I'm not sure about the new VLA because when I did this calculation last, it was before the new VLA. On the other hand, the SKA also has improved since I did the calculation. So I'm not sure if it's still that way or not. Anyway, it's not at all what they're going to do. Big chunks of the time are going to be invested in particular projects for cosmology and so on. So they're not going to do these very broad transient surveys, at least not at the beginning. If you look for radio supernova, which are the most common transient in radio in Google, this is what comes up. I didn't try this. I don't know, maybe it's good. So apparently quite popular, all the top Google hits. But really, radio supernovae are very popular because they are only class of radio transients that is really well understood and also that we keep detecting. And this is what the emission from a supernova in the radio looks like. This is from a paper by Asaf Horesh, a local person here at Hebrew University. And what is seen here are models of the emission in different bands, different radio bands, and what is as a function of time. And what this shows you is these emission peaks at different times, initially at high frequencies and then going to lower and lower frequencies. And that particular evolution from high to low frequencies with this particular shape, which is called self-absorbed synchrotron, and Rehem actually mentioned this yesterday, is quite typical and quite broadly applicable. And this shows you that if you have even a few epochs of radio observations, especially if you have many bands, you can constrain quite a few parameters of the emission. Now, supernovae emit in the radio because they interact with the circumstellar material. Just the explosion itself doesn't emit in the radio. This is synchrotron emission from the interaction shocks. And typically for regular supernovae, the circumstellar material is quite light. So only the fastest ejecta of the supernova are interacting with it, and there's quite a little, it's not a big part of the energy budget of the supernova that goes out in this interaction. There are exceptions. Another thing that usually radio people used to say that radio penetrates everything and you can observe through a lot of dust and see the center of the galaxy. That's all true if the material you are trying to penetrate is not very dense. Now, typically, quite often these supernovae ejecta or also the circumstellar material could be quite dense, and then all the radio is absorbed. So to get the radio, sometimes you have to wait until the material is rare enough so that radio can escape. And another thing that I think will be quite interesting in the next few years about radio supernovae is that high frequencies can escape more easily than low frequencies. And since we now have ALMA, which is this very sensitive millimeter array in Chile, once the management of ALMA is convinced to try to use it for time variable events in target opportunity mode, I think we will start seeing more early detections of transients of all kinds, because I think initially at high frequencies you will have better chances to see them. So the study of radio supernovae is very well established. Typically, for most cases, these studies are not based on radio surveys, so you do not detect the supernova in radio, but rather you follow up on detections in other wavebands. So you detect the supernova, let's say, in the optical, you know where it is, and then you turn your radio telescope there. It could be very sensitive with a small field of view, and then do your measurements. Because not all supernovae are radio sources, actually, to the best of my knowledge, there are no complete surveys of supernovae that tell us really what fraction of supernovae emit in the radio, because it's very hard to convince the observatories to do that, because if you just take, let's say, 100 core collapse supernovae and observe all of them, probably you'll get something like 90 non-detections or something like that, or more. And they don't want to do this investment. On the other hand, because they never do this investment, we don't know if what I said now is true. It's whether it's 90% or 70% or maybe 20%. Well, we know it's not 20%. But so the exact statistics of radio emissivity of core collapse supernovae that do have some circumstellar material with which they interact is really not well established. And I hope this will be solved eventually in recent years, once people convince the observatories to do some systematic surveys, and that eventually will tell us which fraction of supernovae do emit in the radio, which means which fraction of supernovae have extended circumstellar envelopes around them. Okay, let me now show you. Okay, yeah, good question. Tomorrow, this is a good time to say it. I've convinced very easily the management of this school to switch my lectures number 3 and 4. So tomorrow we will talk about supernova types. Because I realized that I talk about a lot about supernovae, and I actually haven't defined what types of supernova they are and all of this stuff. So we will do that tomorrow, and the last lecture will be on progenitors. But to your question, the main types of supernovae are type 1a supernovae that come from white dwarfs, and there are core collapse supernovae and all kinds of other things that come from massive stars. And type 1a supernovae have never been detected in the radio, even though a huge effort has been invested in that. And that means probably that they have very little circumstellar material around them. Typically, right, there might be exceptions. We know there are exceptions, but we've never seen them in the radio. Core collapse supernovae, so most of those detected have been from types 1b and 1c, so those that are poor in hydrogen. But there are some hydrogen-rich supernovae that have been detected in the radio. And when we say detected, this varies by huge factors. Some of them are detected only for a few days at some particular epoch and then disappear, and some of them have been detected for years. And basically, we can follow the process of changing or developing from a supernova to a supernova remnant, because this interaction continues. And eventually, when the slow ejecta catch up and start interacting with a lot of interstellar material, not even circumstellar material, all of them will probably become radio sources. The supernova remnants in our galaxy, the radio emission comes from the Sedov-Taylor interaction, where they, like several solar masses of ejecta interact with several solar masses of ISM. It just takes many years to collect that mass in order to facilitate this interaction. Okay, so in principle, if you conduct a radio transient survey, which means take any radio telescope and observe the same piece of sky again and again, you should find radio supernovae. We know they exist. To the best of my knowledge, the only radio supernovae that was really detected in such survey mode is this, that Eran Ofek and myself and collaborators detected when we did the following survey. So Eran actually came up with this idea. There were two major surveys done with a very large array. One was called NVSS, which covered all of the northern sky. The second one was called FIRST, that covered most of the northern sky with some finer resolution. And he managed which was a very hard problem, to properly compare these two surveys and use this comparison to find transients. And this is the only real transient we found in this comparison, and I think it's a radio supernova. The evidence seems to support this. It was not detected in the optical, so we don't have a spectrum. We cannot prove it's a radio supernova, but all its characteristics suggest that it was. Now, in principle, you can repeat this, and I'm sure that eventually, and VLA is again conducting now large surveys, and people will use this data and compare it with previous surveys, and I'm sure that eventually they will find more radio supernovae in this way. This is very interesting because in principle, especially if you're looking in galaxies, and we'll touch about this shortly, in galaxies that are quite dusty, and you might not be seeing the supernovae in the optical, finding them in radio, especially at late times, would be a very useful way. Okay, so that is one class of sources. Radio supernovae is going to be one class of sources that will be found in radio transient surveys, and as far as I know, this is the only example where it's already been done. Another source that probably should be found is radio emission from tidal disruption events. I'm not going to go a lot into that, but these are observations by Alexander and collaborators. And again, you see the same sort of patterns, these typical light curves moving from high to low frequencies. These are observations of one particular tidal disruption event in a nearby galaxy. And the fact that the same mechanism, theoretical construction is used to model this, basically both assumes and confirms this interpretation that in a tidal disruption event, at least some part of the debris from the disruption of the star is interacting with something in a way that it's similar to a supernova interaction. So fast-moving material is interacting with some slowly moving gas, and it gives you this signal. Also, these, we now know that tidal disruption events are quite, well, not quite common, but they do happen, and we know more or less the rate. So if you conduct all sky transient surveys, you will also find these. Okay. Now the question you could ask is, are there other slow transients in the radio? When slow, I mean day, week, month timescales. And Ranofek in particular, and also myself and other people, try to work on this for a long time. And so there are two more or less famous works on that. One is by Eran and myself. So we found another slowly variable source, which was located here. This is an optical image that shows that there's nothing over there in the invisible light. And there's another more famous work by Bauer et al. That analyzed a big stack of VLA data and claimed to have found many such slowly variable transients. And these are from their paper. So you see, these are VLA observations of some calibration fields that show nothing at some point, and then there's a detection and it goes away again. Both of these works eventually turned out to have been detections of new modes of creating artifacts in the VLA. So none of these sources are probably real. They did teach us to better calibrate VLA data. I don't remember exactly the mode that, the exact artifact that made these things. I do know the one that here was it was an error in the timing of the data readout from the VLA. So what happens is it would observe some field, and then it would start moving to a new field. And because of this small timing shift, the first radio emission from a very bright source in a new field would be still recorded in the file of the old field. So let's say you just move to a very strong source, you get 1/1,000,000th of that flux in your old field, it looks like a weak source in the previous observation. So once we found this, it's easy to correct because you just look at the next observations, and if there's something in that spot in that next image, then it's this. Anyway, so as far as I know, there's no other class except for radio and TDE of sources that has been identified that are slowly variable. Okay. Well, okay. Yeah, I think that's true. The last class of radio transients that I want to talk about before we move to the fast ones are the afterglows of relativistic explosions. This is another class we know exists. It's not been detected as radio transients. It's always been detected as follow-up, but we know gamma ray bursts have radio afterglows. This has been found in 97 in the second GRB localized, and since then has been detected many times. So again, if you do a blind, very wide radio survey for transients, you will also find these radio afterglows. And in principle, if you for some reason miss the GRBs, you can then recover it. This is the only case that I know of where there is evidence that a relativistic explosion happened, and we don't have GRB detections. This is from Senko et al. PTF11AGG. So you see this is a rapidly declining optical source. This is a logarithmic timescale. And then many, like 100 days later, it has a radio afterglow. So the radio afterglow is one of the reasons we believe that this was indeed a relativistic event similar to our GRB, but without gamma rays, because there's no detections of gamma rays. Okay, so these sources also exist in the radio. In fact, for this particular case, the radio was a very important piece of evidence to the nature of this source. Now, the last class, and certainly the dominant in terms of attention in the last few years of radio transients, is called fast radio bursts. And for those of you that are not familiar with this, so let me describe what these are. This is the discovery paper of the first fast radio burst by Lorimer et al., very famous paper now. And what we see here is the flux as a function of time. Note that the time axis is in milliseconds, so this entire time axis is 0.5 seconds. And this is frequency. And the black line here shows there is a transient that goes from high frequency to low frequency and changes dramatically over less than a second. And the interpretation, which has since been supported, I think, quite strongly, is that you have some source that emits a very rapid burst of radio emission. And because this burst is very localized in time, it is going through a dispersive medium, which is either the interstellar material in our galaxy or the interstellar material in the source of the source galaxy of the source if it's extragalactic, or the intergalactic medium in between. And this is dispersive for radio waves. This dispersion causes the pulse to arrive at us at different times for different frequencies. This is what we are seeing here. So immediately this tells us that the pulse has to be very short, otherwise this will be smeared and you will get different frequencies and different times. And it sets some lower limit on the distance, because we know the dispersive properties of material in our galaxy, and we know how much pulses are dispersed when they travel through it. So, and the claim made by Lorimer and since been, I think, vindicated, was that the dispersion here is so strong that it cannot be explained only by gas in our galaxy. It has to come from some other galaxy. There's been a lot of argument about that, but last year there was a localization of one of these fast radio bursts to a galaxy that is far away, redshift 0.2 or something like that. I don't remember exactly. So I think the original claim was correct. So the reason that these bursts are so strongly dispersed is because they are being dispersed not only in the gas in our galaxy, but also in the IGM, and perhaps also in their own host galaxy. Now the detection of this burst, and this burst, by the way, we know from rate calculations. Where is Omer? Here. He wanted to know about rates. So there have been many calculations of the rates of these events. All of them are based on few detections, but these detections have been made within a short time, observing time. So I think there's general agreement that the all-sky rate of these events is huge. It's certainly much more than one a day. So these are quite common. but they are difficult to detect. Why are they difficult to detect? You can see this from this discovery data. You don't know in advance by how much the signal is dispersed. So let's say you read out this cube of data, right? Frequency and time. And then you have to analyze it and look for a signal. So the easiest way to look for a signal, if the signal is not dispersed, you just bunch up all the frequencies together and look for some time variable source. Now, if you do that here, all this signal will be smeared across different times. So the signal to noise, which is quite high in this spot, is going to be smeared with all this noise, and it's going to be much weaker. This source was detected because it was just so strong that probably you can detect it even after you downgrade it in this way. So what should you do if you want to overcome this? You want to what is called de-disperse the data, which means attempt to sum up all this digital data, assuming some dispersion law, and going for all kinds of different dispersion laws until you find the right one, which will suddenly bring up this signal. You can understand immediately, because this dispersion law is known and it's not linear, so you know the shape, but you don't know by how much it's going to be dispersed. That requires a lot of calculations. And the amount of data you can also estimate. Remember, this is half a second of data. Let's say you observe for a few hours. It's a huge amount of data, and you have to do a lot of calculations again and again and again. So in the literature, there were two ways to do it. One was called brute force, which was just try everything. Of course, this becomes computationally prohibitive after a while. And the second thing was try to instead of doing some complicated laws, replace this by some linear function, and hope that over some period of the observation, the linear approximation will be good enough so you can pick up the data. And then once you know the approximate dispersion, then you can do the full thing and figure out exactly. So this prevented actually for a long time progress, because the amount of data depends on how many receivers you work with. So people could only handle data from single dish instruments. Single dish is a big telescope which has one receiver, or at most, let's say, 10 receivers. And these dishes are very sensitive, but they provide only poor localization on the sky. So when you find something, you don't know exactly where it is, and it's hard to follow. You really want to work with interferometers like the VLA, which I showed you, but then this means you have to handle many, many different receivers, and the amount of data goes up. So this problem was also recently solved by Zakai and Ofek, and they presented the optimal dead dispersion algorithm, which is much faster than previous ones. You have to somehow do what they call a modified radon transport. Doesn't really matter. The thing is that it shortens the computation times by like 4 orders of magnitude, which is pretty good. And this is the first example of the application of this algorithm on interferometric data. The data is from ASCAP, which is one of the SKA forerunner projects in Australia. And here you see the data de-dispersed for this particular fast radio burst. You see now all of it has been aligned to the same time. And from this thing, and this is if you sum everything, this is the signal. Now you can see here that the signal to noise here is maybe 10. And if you didn't de-disperse, it means the signal to noise would go down to like 2, which means you cannot detect it. Right? It's much weaker compared to the noise than the previous one we saw. So with this technique, you can now start to find these quite easily. And I think in the next few years, it's going to be a huge industry in radio astronomy. They can find thousands of these events, study them, and localize them, and so on. So I'm sure there's going to be a lot of progress. I would say one thing about the presumed source. I'm not going to go into that because we just finished the amount of time I can spend on this. But the host galaxy of the single localized source so far of this type is a star-forming dwarf. Now, based mostly on this thing, people thought, well, this reminds me of something. What happens in star-forming dwarfs? Gamma ray bursts and superluminous supernovae, so maybe there's a relation. Theoretical work by Waxman and collaborators showed that this doesn't seem very likely. And for these things to escape their environment, there cannot be a dense concentration of gas where the fast radio burst is formed, which doesn't fit ejecta of, let's say, a superluminous supernova that probably ejects like 10 solar masses of material. So I don't think we know really well what's causing these things, but it's certainly very interesting. Yes, maybe we can talk more about this in question time if you're interested. Okay, so that finishes radio surveys. So this is certainly going to be the huge frontier in transients in the radio, fast radio bursts. Very interesting. Okay, going up in energy, we now go to infrared transients. So why should we look in the infrared? Infrared is more difficult to look to observe than the optical. Instrumentation is less sensitive, more expensive. Why should we go there? So the big benefit of infrared, of course, is it's less sensitive to dust. It's also better if you have very cool sources. I think mainly the driver to go to the infrared so far has been to penetrate dust. And it's now maybe 15 years that people have been trying to do infrared surveys for transients in order to find dusty sources, in particular, at the beginning at least, obscured supernovae. And the motivation is you look around us in the neighborhood of the Milky Way, the most star-forming galaxies typically are also very dusty. So most star formation activity, where the most massive stars are and many of the supernovae are expected to happen in very dusty areas. So the idea is that if you observed these star-forming factories that are also very dusty, you can, in very few galaxies, find a sizable or numerous number of supernova, which you don't see because they are so dusty. So I'm showing here a few attempts. This is I think the first one. This is by Maiolino and collaborators who observed some luminous infrared galaxies at the end of the millennium. You can see the supernova over here. I didn't play the game this time. So this blob here is not here. Okay, so maybe this is a supernova. This is from a more recent paper by Matila et al. And they are looking here at two interacting galaxies and describing where the different supernovae happened. The resolution here is not really good, but some of those supernovae have actually been confirmed as supernovae, and some of them are more obscure than some less so. This is ARP 299. And this is more recent work using adaptive optics, which really improved, by the way, this technique. In infrared, you can work with adaptive optics, and then your images become much more sensitive and easier to handle. And this is recent work from Kankare et al., where they found in the same galaxies, see two supernovae, one new and one old. So you see that subtraction, you have a positive and a negative source, more or less of similar luminosity. The light was emitted by the dust. No, I don't think so. Just a second. I have some. These are in the near infrared, so around between 1 and 2 microns. And you just see, I think most of the emission is just the thermal tail of the supernova. It's not yet dust, or not necessarily dust emission from dust formation. That can, when you're saying emission by dust, you mean dust related to the supernova itself. For that, or dust that took all the UV light and reprocess it. Yes. Rebrightening in the dust, right. But then the rebrightening has to do with the temperature of the dust, right? So if the dust, for example, is located far away from the supernova and the emission is spread over a big chunk of dust, it's going to heat up to low temperature and emit in the far infrared. That could also happen, but it's more difficult to detect because far infrared is even more difficult than near infrared. I think in these searches, I think we know because some of them we see in the optical, you actually see the tail of the optical emission. It's true that the emission from a typical supernova peaks in the optical, but the tail in 1 or 2 micron, it's maybe 10% of the optical or something like that, and you still are able to detect it in these nearby galaxies. They are more penetrative, yes. So for these particular events, a few of them, the people estimated the optical extinction, so by how many magnitudes they are extinguished in the optical, and typically these numbers are between 2 and 10 or something like that. So obviously, if something is extinguished by 5 or 10 magnitudes in the optical, it's difficult to detect. But in this near infrared, it could be only by half a magnitude or something like that, and that's you can manage that. So this is the history of that, and now moving forward, the survey that is doing maybe the most systematic work of this type is called SPIRITS. By the leader of that is Kasliwal at Caltech, and we have our own representative here, Jacob, that you can talk to if you want to learn more details. So SPIRITS is using the Spitzer Space Telescope at 3.6 and 4.5 micron to observe a large sample of nearby galaxies again and again. And I'm showing here 2 results, but as I said, because Jacob is here and he's the author of that paper, you should talk to him. So this is a study of extinguished supernovae in some nearby galaxies. This is again in a pair of interacting galaxies. And this is from Mansi's paper, where she defines this class she calls sprites, which are these infrared transients that have no optical counterparts and are less luminous than supernovae. And what they are remains to be fully discovered. So, how are we doing with time? Okay. So this is SPIRITS. SPIRITS has the best song from all projects that I know of, and I will play this song for you if we have time at the end. Okay. Good. Now let's switch to the UV. Well, let me just say maybe one more thing about the IR. All of these surveys that I was describing are biased in the sense that they are targeting specific galaxies. I don't know yet of an infrared survey that is unbiased. So it's just scanning the sky to look for infrared transients. People are working on such surveys, but currently, as far as I know, no results have been published. And this is mainly because wide field arrays of infrared detectors are extremely expensive. So few of them exist. Probably the best one is Vista. And I know that some data have been taken with Vista covering some patches of sky again and again, but as far as I know, no results have been presented. So we don't know actually to characterize the population of infrared transients in general. We know what happens in nearby galaxies. Okay, we skipped the optical because we covered that yesterday, and then that brings us to the UV. So why should you observe in the UV? Again, observing in the UV is much more difficult than observing in the optical because it doesn't penetrate the atmosphere, so you have to go to space. That's a big step, especially in cost. So why is it interesting to look in the UV? It is very interesting, actually, and the main thing that drives you to the UV is, of course, sources that are very hot emit most of the radiation in the UV, and we will discuss this more in a future lecture. And typically, when you have, let's say, an explosion, initially, it's very hot, and then it cools down. So if you want to see things very early on, the UV is where you want to go. And indeed, people have done this and found quite a few interesting things. Let me show you some stuff. So I'm going to focus on the results mainly from 2 surveys, and both of them, or 2, let's say, groups, most of them used GalX, which is, there's a reason for that, and this is because it's basically the only UV detector in space that had marginally big field, about 1 square degree. All other detectors are very, very small. For example, the UV detectors on Swift and other instruments are like very, very tiny. So it's very hard to do any sort of survey with this instrument. With GalX, you could do something. So a big project that was led by Suvi Gezari was called the GalX Time Domain Survey, TDS. And there are many results. Let me show you a few of them. So TDS, or the latest version of the survey was that GalX was observing 40 square degrees. If you remember what we discussed in the optical, this is a small, right? It's a small patch of sky. The ZTF detector in a single image covers 47 square degrees. So all of this effort is equivalent to 1 image from ZTF in terms of area. So 40 square degrees every 2 days, and this went on for 3 years. But still very important work. And the reason it's important is that it provides very nice characterization of the UV transients that exist in the sky, generally. Now I'm showing here two panels. This is showing variable point source. So these are mainly stars and AGN. And what Suvi plots here is the delta magnitude in near UV. So by how many magnitudes the flare was brighter than the quiescent source as a function of the luminosity of the source. And you see different classes. These are RR Lyra stars, so variable stars in our galaxy. This is flares from M dwarfs, this orange one, and you see that many of them are very, very dramatic. So you have 5 magnitudes, so factor of 100 flare from some source, some tiny star in our galaxy. And then there are quasars and AGN, which are variable on all time scales in all wavelengths, including the UV, and provide this very large population here. And CVs, which you can probably hardly see. You can see them better on those screens in this faint cyan. Also have very dramatic flares. These are accreting white dwarfs that sometimes could brighten up by many magnitudes in a night. So these are stellar and AGN, by my definition, not transients. These are real transients. So these are flares that are superposed mainly on galaxies. And so you see that there are quite a few of those. Many of those probably are still some source of AGN, but there are two sources in particular that Suvi here highlights. This is a tidal disruption event, which I'll show you in a second. And this is a supernova that went off in one of those galaxies. Certainly there is a population of transients in the UV, which even with a relatively small survey like that, only 40 square degrees, you already have quite a few examples. Let me spend a few minutes on the discovery of this tidal disruption event, because I think it's a very important result. So for many years, there's been a prediction by Lord Rees, who is also known as Sterl's advisor, that from time to time, that there are supermassive black holes in the centers of galaxies. From time to time, some star would wander into the sphere of influence of the black hole and be tidally disrupted. So this prediction dates back to 40 years ago. And after this prediction was made, every few years, or initially every decade, and then every few years, somebody would find something strange in the center of a galaxy and say, this is a TDE. And most of these things were not very convincing, to me at least, and the reason is that the continuous accretion onto supermassive black hole, which we call AGN, active galactic nuclei, is an extremely diverse phenomenon. They can vary on all time scales in all wavelengths. And whenever somebody tells you, but this is not regular AGN variability, we don't know what regular AGN variability is. They can make all kinds of crazy things, and we've shown this again and again in the past. Somebody shows you a very dramatic flare, you wait 10 years, there's another dramatic flare of the same type from the same source. So calling something a singular event is very hard. Here, however, this was the first time I was convinced that I think tidal disruption events were really discovered in Suvi's paper from 2012. And this is the source. It has a Pan-STARRS name because it was actually picked up in the optical, but there are important observations in the UV. So these are the optical light curves. This is the UV. And the 2 points that Suvi made at the time was that it brightens up slowly, declines weakly. It doesn't change its color and temperature. Now, if you think about a regular explosion like a supernova expand. So it's very hard to keep them from cooling. Right? Imagine something starts as the size of a star, 10 to the 12, 10 to the 13 centimeters if it's a big supergiant, and then starts expanding at 10,000 kilometers per second. So it doubles its size in hours, and then again and again and again. It must cool very strongly. So it's very hard to keep something like that not cooling for hundreds of days. There must be some master process there. So that was one argument. Here they compare to this theoretical prediction that the rate of decline should go down like t to the minus 5/3, which is theoretical prediction, and actually not too bad here in the data. But to me, the most convincing was the spectrum. And the spectrum here which is this black spectrum, can be deconvolved into three components. A hot thermal black body, the spectrum of the host galaxy, which of course is there because you are looking at the nucleus of a galaxy, and the spectrum of the transient, which is dominated by two emission lines of helium-2. And this is something we've never seen from a supernova in a persistent way. So the fact that you have this for weeks helium-2 emission, which means that helium is ionized, it's exposed to a very hard ionizing spectrum, we've never seen in any supernova, and actually also not in AGN. So to me, this was a convincing demonstration that this is something else. And indeed, I think eventually Suvi's work and also Yair Arkavi's work provided convincing evidence that there's a class of events that are really good candidates to be tidal disruption events in the centers of galaxies. And this initially came from this TDS, the Galaxy Time Domain Survey. Yes? Very good question. There's a huge amount of work, including a lot of theoretical work here in Jerusalem. There are bagel models and spaghetti models, and I don't remember what other kinds of food. So if you imagine throwing a star into the supermassive black hole, it's being disrupted, and then the ejectors start making all kinds of weird motions, not weird, complex motions. And what part of the ejector emits what radiation at what time is still very much an open area of study. There are some models that begin to recover these observations. There's still quite a bit of argument, I think, in the community, what part and at which time emits this radiation. So I think theoretically it's not answered. There are components like you have these streams of material. They could interact with, a stream could go on and then cross itself and interact with itself. It could interact with an accretion disk. There would be all kinds of shocks and hot parts of this ejector that can emit all kinds of components. And at least I don't know to say what's the answer to your question. Tzvi, maybe he's not here, I think, right now, but certainly has one of the leading models for that, and other people have other models. So it's a very, very interesting question. I think theoretically it's quite juicy. So I don't know the answer yet. But the observations are, I think, at least the observations become consistent. So we have now a class of objects with many examples that have similar spectra that only happen in nuclei of galaxies and never happen anytime else, anywhere else, which means they must have something to do with the nucleus of the galaxy, and so on. Okay, so that's about TDEs, very, very interesting subject that sort of grew out of these UV transient surveys. Next thing that I will talk a little bit now, a little bit later, and a little bit in the fourth lecture on is an early UV emission from supernovae. Again, I'm showing here an example from Suvi's work, which is this Pan-STARRS supernova that was also detected in the UV. And you notice there are detections in the optical. They are sort of flat in red bands, going down in the blue band, and the UV is dropping very rapidly. And this is a typical behavior for a supernova, okay? Initially, it's quite hot. It has a lot of UV emission, but this emission falls dramatically in the first few days. And this is because typically these things are well approximated by black body. So the black body peak moves through the UV band. So as long as it's at or above the UV, you have a lot of UV, but as soon as it moves below the UV band, the UV just drops like crazy. So typically, this is a very typical behavior, right? A flare in the UV, and after which you get an extended emission in the optical. So the UV initially dominates the bolometric luminosity, but only for a short period of time. Now, exactly how to interpret this early emission is a big subject, and we will talk about this later. So this is all the results I wanted to share from this particular survey. Let me show you two other things we did with PTF. So Eran Ofek had this very smart idea in 2009, 2010. So GalX was observing then, and GalX was observing in all kinds of patches of the sky for different surveys and different people. And the locations where GalX was observing were known. So what we did with PTF was we shadowed where GalX was observing. In the parts of the surveys where we didn't care where we were observing, we just said, okay, what's GalX going to do tomorrow? Observe there, let us observe there also. And what it created was the opportunity to have 3 UV observations from GalX of supernovae you detect with PTF. And this is maybe the most interesting result from that thing. So it's the wrong name. So it's called PTF 2009 UJ. So Ran published it in 2010. And the thing I wanted to show you here, so the red is observations from PTF in also the blue. So this is the supernova going up, going down in visible light, nothing special here. But if you look in black, these are observations from GalX, and you see they are rising, and this is over quite a bit of time. So this is very different from what I just showed you. Right? The UV is still going up. This is immediately telling you that this is probably, the supernova is not a regular supernova where you have a hot ball of gas expanding and cooling. Indeed, this was a type 2N supernova, so there's some interaction with material around the supernova. This allows you to explain how the UV continues to rise. And to do this, Ran actually developed the concept of shock breakout from a wind. And since then, it was also already studied before, but since then, certainly it's been well studied here and in other places. So it's a very interesting subject, also theoretically. And this was, I think, the sort of spark that lit this piece of study. Another thing we did with PTF in 2012, and this is from a paper by Ganot et al., which apparently I didn't write. So in 2012, GalX was basically decommissioned by NASA. And there was this strange situation where it was a perfectly good satellite that could observe in the UV, but NASA didn't want to run it anymore. And they were basically willing to rent it to people. So if you wanted like a UV satellite and you are willing to pay $1 million a year, so you could have it. So, okay, we didn't have $1 million, but we raised up some money with our I don't remember, it was $1 million, yeah, something like that, $1 million a year. I don't remember exactly the price. But we managed to buy something like 2 months of GalX time. And during these 2 months, we did the following experiment. We scanned the patch of sky again and again in the UV, and we scanned the same patch of sky with PTF in the optical. So basically, we repeated what Ran was doing in 2009, but now in a designed fashion. And we did this for 2 reasons. One, it's interesting to see what sort of UV emission you get from supernovae early on. But mainly, we did it as a pilot for a space mission we are planning, and I will tell you about in a few minutes, called Ultrasat. And this was basically some sort of very, very poor man's Ultrasat, so that we can try to have an experience, what should we expect. And indeed, we detected 6 supernovae. And you see the same thing that we saw before in most of them, which is, so this is time in days, and this is UV flux from GalX. There are 6 examples here, and usually what you see is nothing, then the sharp rise, and then rapid decline in a few days. So these are all typical supernovae. The star explodes, you have this hot ball of gas, it expands, cools, the UV shoots up, falls down. So Ganot et al. Presented this, and now he's working on interpreting this data. And Adam Rubin, who is also here, spent a lot of time thinking about what you can do with these UV light curves and optical light curves, and we can talk about this in a future lecture. There is one unusual supernova here, and this is this one. And let me jump to the next slide where you can see this better. So this is from a paper in preparation by Maayan, who's sitting here. And you see for this particular supernova, so there are non-detections or very weak detections, and then the optical goes up, but the UV also goes up, and this is for 1 month. So we have a rising UV light curve for 1 month. Again, this is inconsistent with any sort of cooling. So it must be something else. And again, we see from the spectra, and also you could guess that this is some sort of interaction with massive CSM. Still, there are puzzles here, and Maayan can tell you about this paradox we are left with. Basically, the strange thing is here is that the fact that the UV is rising for so long means that the luminosity is rising, and the temperature is falling only by a little. And that means that the radius of the emission, because it's close to black bodies, should be increasing. Now, in principle, if this was a supernova, you would say, yeah, sure, of course the radius is increasing. But if you are interacting with CSM, this is not what you expect, because the shock that is interacting with the CSM, typically, and this has been observed in the past, is more or less in a constant location, because it's very, if you're spending all of your energy pushing through very heavy CSM, it's hard to expand, certainly not at high velocity. And here, the velocity of expansion of the shock is quite large, or not the shock, or whatever it is that is expanding. So exactly what's going on there in the CSM is still very much open, and Mayan is working on all kinds of analysis to try to figure that out. But certainly, and this is one of 6 supernovae we observed. So I think with the UV surveys, certainly we will have many, many more events like this. This cannot be a rare occurrence. So it must be quite common. And probably tells us that we don't really understand that well what happens with circumstellar material around massive stars, which will not be a big surprise to people that study this subject. Okay, so this is very interesting. This is from the GalXPTF campaign. Actually, there are some additional interesting results from that, but I don't have time to go into them. So this is more or less what we learned from these UV transient surveys. Now, okay, one thing, so okay, we'll stop with this PTF surveys. The last thing I wanted to tell you before going to speak a little bit about ultrasat is of course to mention the recent discovery of the kilonova associated with the binary neutron star merger detected by LIGO, which was also a UV transient, in the sense that early on it had UV emission, and because we don't have a record of the first few hours, we don't really know, but I think every reasonable assumption leads to the fact that initially it probably was dominated by the UV. When we first detected, the UV is more or less comparable to optical, but I think it was certainly hotter in the first few hours. So at least based on this one event, GW kilonovae are UV transients. Okay, which leads me straight to telling you about ultrasat. So ultrasat is a concept that we've been working on now for quite a few years, actually, unfortunately, because the idea was to build a small satellite that we can rapidly build and go to space. So we've been working on this for a few years, which means it's already not very rapid. But still, it's quite, I think, an attractive concept. So this is a collaboration of scientific institutions, so the Weizmann Institute in Israel and Caltech in the US, NASA, the Israeli Space Agency, and a lot of other important industrial collaborators that we need in order to build all of this fancy hardware. So the concept is, and if you think about this, it's basically never been done, to build a small scientific satellite that is small, lightweight, cheap, and you can rapidly build it. There were attempts to do it, and we are trying to do it, but I think something like that exactly has never been done. So this box that we see here, which is the concept for the satellite, it's not a concept, it's actually an engineering design. So we can build a box that looks exactly like that, and we'll do the science that we want to do. It's less than a cubic meter, and it's about 100 kilos in weight. So we can easily put it here. And it's compared to other satellites that cost hundreds of millions, if not billions of dollars, this is much less. The project cap is about $100 million, including the launch and all the things around it. And the capabilities are quite fantastic. So it has a field of view of 200 square degrees. So that's 0.5% of the entire sky in every image, to a sensitivity that is somewhat better than that of GALEX. So you remember all the results I showed you from GALEX that worked with 1 square degree. This is 200 times better, just in field of view. And it's even better because it's a bit more sensitive. So you can do all kinds of stuff. You can do, for example, cover the entire sky if you really wanted to, which is not what we plan to do. But if you just stare at a single location in the sky, because the field of view is so huge, transients will just happen in your field of view. You don't have to move anywhere, which means you will see each transient from the moment it starts happening. So we will really, for the first time, see these transients in real time. So we're talking about stellar explosions and gravitational wave counterparts and all of that stuff from minute one. Not, we found it with some other way, now we move and until we reach and get there. It's just going to happen in the field of view. And this is a totally new concept. And it's really very, very powerful scientific wise. Let me show you a few slides about that. So as a transient engine, this shows you the volume of space you can cover with a survey for hot sources, right? Something which is as hot as 15K or more. And this compares Ultrasat with everything else that's on the ground. This is GALEX, and as we said before, it's no competition. It's much more powerful. But even if you compare it to LSST, which we discussed yesterday, it's going to be a very powerful ground-based survey. Ultrasat is going to be comparable or better than LSST. Of course, for hot sources. If you're interested in infrared sources, Ultrasat is not going to help you. So it's going to be much more powerful than anything else. For anything that emits basically in the blue and UV part of the spectrum. Yes? Does not take dust distinction into account? Yeah, it does. Okay. Well, okay. It does in the following sense. For example, when we calculate the number of supernovae that we are going to observe, this is exactly why we did this GALEX pilot thing. So we are using statistics from UV observed supernovae that are already have been extinguished by dust, if it's there or not, to calculate this. So this is only based on sources that we already saw in the UV. Of course, we'll be missing some population of sources that are dusty, but they don't go into this calculation. So in that sense, it's dust corrected empirically, right? We don't assume anything about how much dust there is and extinction laws and all of that. It's just based on the number of supernovae we see in the UV. What could this do for supernovae? So here are models of different progenitors exploding as supernovae, red supergiant, blue supergiant, different types of ultra-A stars, and their expected emission in the UV as a function of time. This is a logarithmic time scale, and this is 1 day. So we are talking about very early emission, before 1 day, starting at 900 seconds here. And this is the expected sampling you would get from Ultrasat. So we will be covering this temporal range in a way that's never been covered. And you can see that distinguishing different progenitors is going to be trivial. Right? Is it this or this or this or that? It's not going to be difficult to say. Of course, then you can say, well, if it's a red supergiant with a radius of 500 or 600, can you distinguish, yes or not? And Adam Rubin studied this quite extensively. But the basic question, what sort of star explodes as a supernova, we will answer easily. It doesn't require any subtlety at all. So this is what it's going to do for massive star explosions, and we'll talk more about this in the fourth lecture. But maybe the more juicy part, especially now, is how is it going to do with detecting gravitational wave sources. So we made this slide before. Actually, Stern made it before the GW event was discovered. But it's just predictive, right? So it's like exactly what happened. So this is the field of view we sort of expected for LIGO plus Virgo. And the actual localization of the GW kilonova was actually a bit better than what we plotted here. And this is covered by a single field of Ultrasat. Now, Ultrasat can point into any place in the sky within minutes. So as soon as you get something from LIGO, 5 minutes later, Ultrasat can be there, staring at this location. So we can have continuous coverage of that location from the moment the merger goes on to, I don't know, a long time later. And we will know what happens in the UV immediately, and we'll be able to localize it and tell the community where it is also immediately. And this is true for about 50% of the sky, a bit more. We cannot observe toward the sun. Most other people can't observe toward the sun either. So this is this exclusion area where the sun is. But the rest of the sky we can point to. This is actually quite fantastic. On the ground, the only thing that is Marginally close to that is these networks of ground-based telescopes like LCOGT or Growth that have telescopes on all continents. So regardless of time of day, the hope is you will be able to point some telescope over there. From space, of course, you don't care, right? If it's not near the sun, whatever time of day is, you can observe. So Ultrasat can find all of the GW events up to 600 megaparsec based on the emission from this one easily. We will have an all-sky coverage with Ultrasat as reference, so we only have to go there, see if there's something new, and that's it. But the interesting thing, the field of view is so large that based on the rate from this LIGO event, which of course has a large uncertainty because it's Poisson statistics on 1, but based on this rate, Ultrasat will be able to blindly find kilonovae at the rate of 20 per year, that even those that are outside of the sensitivity range of LIGO and Virgo. So let's say a kilonova goes off in a galaxy 500 megaparsec away, LIGO will not see it, we will be seeing it as the optical or UV counterpart. And also we will have untriggered events for LIGO. This is interesting because if you tell LIGO the time and place such an event took place, they can go back to their data. Right now their sensitivity is extremely high. They require a signal to noise of 8 sigma in order to trigger. But of course, there are plenty of signal below 8 sigma. And if you tell them, did you have something at this consistent with this location on this particular minute or hour, they can go down and recover it at much lower significance. So basically, it can boost up the number of detections by LIGO. So this is, I think it's quite fantastic. Okay, so as you can probably feel, I'm pretty excited about this mission. And I hope we are pushing now very hard to try to get it to space in the next few years. Okay. Yes, question.
So is all the data in blind serving them, is all the data just transmitted to?
Yes, right. So Ultrasat is built so that all the pixels are transmitted continuously to the ground. Right. So you can do ground analysis within a few minutes continuously. It's a requirement from the satellite. We solve this, if you are a little bit, for example, familiar with Swift. Swift also has these rapid observations, but the problem with Swift is that it has a single ground station, and it goes around the Earth every 1.5 hours. So sometimes there's data on the satellite, and you know what observations have been taken, but it will take at least 1.5 hours and sometimes several hours until it is downlinked to the ground station. And this is because it's in low Earth orbit. Ultrasat is designed to be at or close to the geostationary orbit where communication satellites are. So basically it's above a single ground station all the time. So you can transmit this ground station continuously and you don't have this limitation. And alerts will be distributed immediately also. Yes. More questions? Okay. If you have spare $1 million to help with this mission, let me know. Okay. Okay, and now in the last few minutes, the thing that's left is to cover X-ray and gamma ray transients and a few other things. So we'll do it very rapidly. So X-ray transients. So when people say X-ray transients, and if you Google it, usually they talk about galactic sources. So neutron star sources in our galaxy, or sometimes they're all mostly neutron stars that are transient. And this is, how do you see it over there? Oh, it's much better here. So this is how it looks from ROSAT, right? So you point at some location on the sky, you have some strong X-ray source. This is SMC X1, the strongest X-ray source in the Small Magellanic Cloud. And then you look again, and there's another source next to it, which is much stronger, and then it disappears, right? And these are just transient accretion or other phenomena on neutron stars, which is quite common, and we will not discuss it anymore. So when I say X-ray transient here, in this context again, I'm talking about extragalactic transients. And there's actually been a lot of effort to characterize these classes of objects with these different missions. So this is ROSAT, which sort of started all of this. Swift, we've discussed with these many different instruments. XMM Newton. XMM Newton is an interesting case. So XMM Newton is a very sensitive X-ray telescope. It observes here. And then let's say it observes here, and then it wants to go there. So it turns. And because it's not moving very rapidly, because it's a very long satellite, during this slew, it actually continues to collect data on a strip of sky that is determined by the end point and the beginning point. And all of these data are conserved and transmitted, and people are actually looking for transient in this, they call it the slew survey, and have found several interesting transients in this way. So just by XMM Newton not observing your location, but actually moving there while it's going from point A to point B in the sky. This is Maxi, or actually, this is Maxi, hanging down from the International Space Station. It's a X-ray detector on the ISS, and it's omnidirectional. It doesn't have, or it's observing a lot of the sky. It's not omnidirectional. Okay, it's scanning a lot of the sky a lot of the time, and finding some transients. And Anna is working on those. And that's Chandra. So Chandra is maybe the most, not maybe, currently the most sensitive X-ray telescope there is. Very small field of view, but still they managed to find transients even within this small field of view, and I will show you an example later. Okay, so let's begin with this. This is maybe the most famous X-ray transient, extragalactic, which is supernova 2008D. This work by Alicia Soderberg and collaborators. And this is really like the jackpot. So Alicia was observing a supernova in this galaxy. You see this supernova here. And then she was observing it again and again with Swift to monitor the UV light curve. And then while this was going on, and Swift was observing this supernova, and the chances for that are really slim, another supernova happened to go off in the field of view of Swift at the exact moment it was observing the other supernova. So this supernova was ongoing, and suddenly this thing goes off. And this is how it looks in X-rays. Right? It's a huge flare of X-rays. So when Alicia looked at the X-ray data, I sort of noticed something was going on. And it's really a great discovery. And this is how the X-ray flare looks like. It goes up, it goes down quite smoothly. And I think, at least in my opinion, it's very likely the shock breakout from the star. So this is something, did we talk about this? Not yet. But we certainly will discuss this phenomena. So, okay, the star exploded, you inject energy in the center, a shock wave goes out, and when the shock breaks out from the surface of the star, you get a very strong flare. And I think for this particular case, this is what we're seeing. Now, you can say, well, okay, Alicia was very lucky. Can it happen again? The answer is yes, in the next decade or something. Yeah. So you really, Swift is still observing many, many things. So eventually something else will happen in the field of view. But the field of view is so small that it's extremely unlikely to happen again until your grad students sit here in the next winter school about transients.
So these lower left panel showing the X-ray image?
Yes, that's the X-ray image.
So what is the right light curve? So is that for the...
That's visible. It's actually visible UV combination. This one, yes. That's the X-ray light curve.
For which one?
For this one.
So why the error bar is compared to the?
This is an integration of all of this data together. Right here, there's time resolution, which is very fine. You see, this is time scale in seconds. So once you bin this into something less fine than seconds, you get a very strong signal. So Alicia did that in order to get the temporal behavior, which I think is quite well characterized. Okay, so this is a very rich thing, and of course you would like to find many more such events. They tell us a lot about stellar explosions, but Swift is probably not the right instrument. Of course, what you want is a similarly sensitive instrument with a much wider field of view, and that's hard. You know what's the main problem with, maybe you should just say it for general knowledge, why is it hard to build a sensitive X-ray telescope? So do you know the answer? What was it? Yes, right, the optics. So how do we build a wide field instrument in the optical? We build a telescope that has the correct optics to image a big patch of sky onto a big detector. And for that, we need to apply strong deflections to the light rays, right? Now, in X-rays, we cannot do that. So X-ray optics only know to make weak deflections by grazing incidence. So you cannot image a big field of view onto a big detector. In order to do that and keep all of this field in focus, you have to have strong deflections. So there are two ways that people do. Either they build small detectors that are fed by very distant optics with small angles. This is what Chandra does, for example. Or you build non-directional detectors. You take a big chunk of X-ray sensitive, let's say, how do you say it in English? And anyway, an omnidirectional detector, and it tells you, yeah, some X-rays went from there or from here, but it cannot tell you the direction. And this is still not solved. So it's very hard to build the wide field X-ray detectors. And E Rosita is probably going to be the best attempt so far, but we'll talk about it. Actually, I don't think we will talk about it. Anyway, okay, so this is this thing, certainly something we want to do in the future. Another type of X-ray transients, which is quite well known, are called X-ray rich GRBs or X-ray flashes. So these are similar to gamma ray bursts, which have been discussed yesterday already, and I will say one thing about them in the future, but at low energies. So like you have a gamma ray burst, and then you have a soft gamma ray burst. So if it's extremely soft, it becomes an X-ray burst. And this is one example like that, XRF from February 18, 2006, quite famous. So this is the X-ray flare, and then later on you see a supernova over there. And it's obvious this phenomena, at least some examples of this phenomena are probably closely tied to gamma ray bursts, at least the low luminosity branch. So these are found by these, basically by these gamma ray satellites. And finally, let me show you this single transient that was discussed extensively by Bauer et al. And this is an X-ray transient found by Chandra. Now, we just said that Chandra has a very tiny field of view. And indeed, it was observing a patch of sky called the Chandra Deep Field South for 2 million seconds. Right? 2 million seconds. How many seconds in a year? 3 million. So 2 million seconds, Chandra was observing a small piece of sky. And of course, this is a very well-studied piece of sky. They observed it with every other telescope conceivable. And in that data, Bauer searched for and found an X-ray transient, this one. So an X-ray source that appeared and was not there. Of course, it doesn't appear in the entire 2 million seconds. So you have some observations, nothing, and then there's a flare, and then it goes away. And you can see this here. So these are the counts. Goes up and goes down. Now, these are, by the way, the real counts, right? So you see, in X-rays, it's very nice because the background is really very close to zero. So something that's 20 counts, so actually 20 photons, is extremely high signal to noise, right? There's no doubt something is going on. So something goes on a time scales of like sort of minutes, and then it disappears. And then because there's a wealth of other information, this paper spends a lot of time trying to say what it was. There is a source there, you can see it here. It's probably a distant galaxy. So something in that galaxy emitted a burst of X-rays for a few minutes and disappeared. And what it is, well, we don't really know. But the fact that it happened in such a tiny field of view means it cannot be very rare, right? If you had sensitivity like Chandra over the entire sky, you would see this, I don't know, every day or something. So there's a class of transients like that are very common, but for us very difficult to see because you need a very sensitive X-ray telescope, which you don't know how to make for the entire sky. Okay, so I think I'm running out of time. Let me just say one thing about gamma ray bursts. So this was already discussed, and I think there's not much use in me discussing gamma ray bursts because we have many lectures about that. But there are many classes of gamma ray transients. So there are long gamma ray bursts, low luminosity gamma ray bursts, short gamma ray bursts. There are flares from soft gamma ray repeaters in nearby galaxies that we sometimes see. And there are these ultra-long gamma ray bursts that are not well understood. And then there are some tidal disruption events, so people think, that have, during this disruption process, also managed to launch a jet, and then you would see them as relativistic gamma ray sources for a long time. This is from a paper by Levan et al., and you can read it or many other papers to learn more about these different classes. Let me spend the final few moments to say one thing or two things about neutrinos. So far we've been discussing electromagnetic transients. Now we have two types of non-electromagnetic transients. One are cosmic neutrino sources. So, of course, the most famous one is a source of what we call low-energy neutrinos, MEV neutrinos, which is supernova 1987A. I don't know if you know that, but the Kamiokande, which is the most famous detector that detected 87A, started to run 1 month before the supernova went off. So they started January 87, and February, supernova 87A happened. Of course, they were quite happy. And since then, the detector is running, and there are no additional sources for 30 years. So people have, grown old and retired and still waiting. Okay. And the problem, of course, with these things is that the sensitivity of the detectors is such that you can only detect either supernovae in our galaxy or at most the local group. And the rate is just very late. So on the one hand, they were maybe very lucky. On the other hand, how frustrating. Okay. One point I wanted to make, this is from a recent paper by Bloom and Kushner. For many years, many people, including myself, said, okay, the fact we saw neutrinos from 1987A means that there was a neutron star formed there, and that means that some core-collapse supernovae produce neutron stars. Now, this paper shows that it's actually not correct, and you can certainly have this neutrino emission from the proto-neutron star that leads to eventually a black hole. So the fact we saw neutrinos from 87A doesn't mean that necessarily core-collapse supernovae make neutron stars. They can also, in principle, if somebody has a model that all of them makes black hole, it is not inconsistent with 87A. So the next galactic supernova, the neutrino detectors are going to have so much information, and we'll learn really, I'm sure, a lot of information about how stars explode. Okay. Final slides. High energy neutrinos, Ice Cube in the South Pole is observing, and Nora over there is an expert in that. You can ask her. This is from a paper that she wrote, appeared at Artsen et al., and shows the coincidence of high energy neutrinos with a supernova from PTF. Probably not significant. It's a chance, maybe quite likely a chance correlation, but still, it's interesting to try to figure out what is the source of astrophysical neutrinos that Ice Cube is detecting, and we know it is detecting some class of astrophysical sources. And I will leave you with this rhyme. Okay, thank you very much.